brittle fracture analysis of dissimilar metal welds between low alloy steels and stainless steels at low temperatures.
Thank you, Mr. Chairman. So, hello everyone. I'm a PhD student from Framatome, France, and I will be talking about an experimental study on brittle fracture analysis of dissimilar metal welds between low alloy steel and stainless steel at low temperatures. So this study is part of the ongoing research in the nuclear field aiming to extend the operating nuclear power plant's lifespan to 60 years. And so we have to show to the good integrity for each component under normal and accidental circumstances. And the focus of this study are what we call stainless steel dissimilar metal welds, which are very critical components when it comes to integrity assessment. So these what we call them SSDMW are welds connecting in the primary circuit. So so they connect low alloy steel main components like the power vessel or pressurizer to the austenitic stainless steel piping. And as you can see in this photo, first of all, we perform what we call an austenitic buttering. So it consists of several layers of austenitic steel deposited on the ferritic component, and then we perform the main TIG welding between the austenitic buttering and the austenitic stainless steel piping. And as you can imagine, the biggest heterogeneities when it comes to microstructure or mechanical properties are concentrated in this interface between the ferritic component and the buttering. So in the rest of the study we will focus on this interface. So the problem with this SSDMW is that when it comes to the study of its fracture resistance, we have a lot of dispersion, as illustrated here in this toughness temperature diagram obtained from an experimental program on CT specimen with this geometry. And we see that we have much more important dispersion than what we are used to for the ferritic base metal. So this emphasizes the fact that it's a very heterogeneous microstructure and that classical engineering approaches like the master curve don't work for this structure. So in these conditions, how can we build a model to predict the risk of brittle fracture failure? So to answer that question, here are the outlines of my work. First of all, we start from the microstructure level, and we study the different microstructures we have across the interface in order to identify the weakest zone for brittle fracture. Then an analysis of the fracture resistance with toughness tests is required in the brittle to ductile transition domain. And we will identify the brittle fracture mechanism which is involved. And then we will try to come up with probabilistic stress-based model to predict the risk of brittle failure for this SSDMW. So let's start with the microstructure. Here you can see a same image of a polished and etched specimen, and we can see the different microstructures across the ferritic buttering interface. So we can see it very well, but on one side, on the ferritic side, we have the ferritic heat-affected zone, or HAZ, which is characterized by its banitic microstructure. And on the austenitic side, we have the austenitic buttering characterized by an austenitic microstructure with residual ferrite delta. between the two layers, we have the interface, which is composed of fully austenitic zone, so without residual ferrite delta, which results from a primary austenitic solidification mechanism during welding. And we have, close to the ferritic, has a martensitic layer just here, which results from a combination of two mechanisms, so rapid cooling subsequent to welding and the local chemical composition, which is given here in this EDS profile. So we can see that our martensitic layer has a chemical composition which is mainly ferritic, so 80% ferritic, but we nevertheless we have some chromium and nickel element which comes from element diffusion during the welding. So now let's analyze the carbide distribution across the interface, and we can see that there has been some carbon diffusion from the ferritic side to the austenitic side, creating one decarburized layer, decarburized has in the ferritic side, and causing carbon enrichment of a narrow band composed of the martensitic layer and the fully austenitic zone, which we will call hard layer. So composed of carburized martensite and austenite. And the micro hardness profile across the interface shows that, we have an important local hardness gradient in the martensite austenite interface, which we will call MA interface, so very different from the MA constituents which were introduced previously. So a large population of defects in this interface, especially at the grain boundaries, and combined with very heterogeneous microstructure, we can conclude that the ferritic buttering interface is a potential weak zone in the SSDMW. So now we will try to characterize the fracture resistance of this SSDMW. So we performed an experimental program on CT specimen, and the first objective was to characterize the fracture resistance of the ferritic has. So we aimed mechanical crab tips in the ferritic side very close to the interface. And as I said before, we can see that we have an important dispersion in the brittle to ductile transition domain, and we have very low toughness values, even though we are close to the upper shelf of the transition domain. So, we have to do some analysis of the fracture surfaces in order to understand the underlying fracture mechanism responsible for these differences between, for example, this value and this value at the same temperature. So, first analysis of the fracture surfaces shows that because of the unevenness of the MA interface, which we see right here, for some specimen, we obtain mixed fatigue pre-crack. So fatigue pre-cracks with both austenite and ferrite. And that most certainly will affect the crack initiation and propagation. So, and when we try to link the composition of the fatigue pre-crack to the toughness values, we notice that the lower toughness values are always for specimen with mixed fatigue pre-crack, as we can see here. And on the other hand, the higher toughness values are for specimen with fatigue pre-crack only in the ferritic side. So we can conclude that the presence of austenite in the fatigue pre-crack plays a major role in toughness lowering. So SEM analysis is required to understand what role plays the austenite in the fatigue pre-crack. So we take a low toughness specimen and we analyze the austenitic parts of the fatigue pre-crack, which we see here, and we see that the failure of the specimen, so as we expected, initiates in the austenitic zones of the fatigue pre-crack, and that the brittle mechanism which is involved is intergranular fracture, as we see here. And we can see the coarse grains boundaries in this fracture surface, which are characteristic of the former austenitic grains of the martensitic layer. So this brittle mechanism initiated at the MA interface. So I don't have enough time to show you the higher toughness specimen, so I will just show you a schematic representation of the different failure mechanism for the two configurations. So for the low toughness specimen configuration, we start from the fatigue pre-crack, which is in the austenite. Then we have crack deviation towards the MA interface with ductile tearing. Once we are there, we have intergranular fracture initiation, and then the crack deviates toward the ferritic has with cleavage fracture. For the high toughness specimen, on the other hand, we start from the fatigue pre-crack, which is in the ferritic has, and then we have some ductile tearing in the ferritic has, and the brittle fracture initiation is done with cleavage fracture. So now that we have shown the role played by the presence of austenite in the fatigue pre-crack, we can take the toughness values analysis one step further, and we can sort the different specimen based on the proportion of austenite in the fatigue pre-crack. That's what we see here, the different values. And we can see that there is a clear disparity between specimen who have austenite in the fatigue pre-crack, so red and green, and specimen with only ferritic steel in the fatigue pre-crack in blue. So which emphasizes the fact that the weakest zone in the SSDMW is this MA interface. And furthermore, we can see, if we look just here, that we have some kind of plateau at low temperatures, which is consistent with the notion of threshold toughness or threshold stress. So which is the stress below which intergranular fracture of the DMW interface cannot occur, which is widely introduced in the literature. So a 3-parameter Weber critical stress-based model seems a good choice to model this brittle fracture. So
2 minutes, please.
Sorry?
2 minutes, please. Thank you.
So in the last part, we will focus on the identification of the threshold stress. So a suitable way to do so is by testing notch tensile specimen at very low temperature in order to minimize the plastic deformation. And we have to choose the geometry configuration which promotes intergranular initiation at the MA interface. The second step is to do a finite element analysis of this NT specimen in order to calculate the maximum principal stress at the MA interface at fracture for each test. And finally, we try to fit the data with the 3-parameter Weber law in order to calculate this threshold stress. So to choose the best configuration promoting intergranular initiation, we tested 3 different positions of the hard layer in the notch. So these are the 3 configurations. The first one concentrates stresses in the ferritic has, so seems to promote cleavage fracture in the ferritic has. So it's not suitable, as we can see here. So very limited intergranular fracture. The second one seems to promote intergranular fracture, but concentrates stresses in the hard layer and not in the MA interface. So as you can guess, we chose the last configuration, which seems to promote intergranular fracture in the specimen boundary and concentrates stresses in the MA interface. So we did 5 more tests with this configuration, and for each test we calculated the maximum principal stress at the MA interface, sigma interface, and then we ranked the different specimen with increasing stresses, and we fitted the data with a 3-parameter Weber law, which you can see here. So, and this is the 3 parameters obtained, and so we can see that we have very low values for the Weber modulus and stress and distress. So this comes from the fact that it's 3 parameters and not 2 parameters Weber law, and also from the unevenness of the MA interface. And this value of threshold stress is consistent with the maximum principal stress profiles we obtained for the CT specimen simulations, which I don't have time to show you here. So here are some conclusions and upcoming work. So we showed that in the SSDMW, the weakest zone is this hard layer composed of carburized martensite and austenite. Fracture toughness tests carried out at low temperatures showed that this hard layer is a weak zone, showing intergranular fracture initiation at the MA interface. And this fracture mechanism seems to be consistent with threshold stress. So in the last part, with the 3 parameters Weber law, we modeled this brittle mechanism and we identified the threshold stress, this value. And so to complete this work, we have to identify, of course, the other Weber law parameters, which may be temperature dependent, so have to be identified with CT fracture tests in the brittle to ductile transition domain. And so, of course, we have to apply this probabilistic model to other geometries, so SENT specimen, and eventually to a real structure case. And last point is that, as I said in the introduction, we have to study the effect of thermal aging, since we want to extend the lifespan of these facilities. So we have to study the effect of thermal aging on the DMW by some heat treatments we do, and we study the effect on toughness and on mechanical properties. Thank you for your attention.
Thank you very much.